So today I tried to give a talk. I prepared lectures 3 times. So each time I have a different idea. So finally I decide I will give a full account. I mean, at least I will state the full generality of the Gross-Zagier formula. That means that I will not go to the classical one. I will not spend much time, but maybe I will spend some time to talk about the relation between the Gross-Zagier's original work. If you want to see that the history of the application, or whatever, you can see that I just put a paper in my web a few minutes ago, probably 1 hour ago. So this is, I don't know, you go to www. Columbia.edu. So I put a paper. It's basically is a survey paper. For the talk I given at MIT Harvard series, and the other one include a lot of result of Dalmon, Bertolini, Cornu-Vaza, and Mazur's conjecture. So it's and today's talk is based on 2 papers. I mean, the references. One's Annals paper, one's Asia Journal, Asia Journal Mathematics Journal, and also include a new simplification. So the result I will state today should be simpler than the one given by Asia Journal of Math. And I was pushed very hard by Gross. These people, they said the result I put in Asia Journal is too complicated. So, but this is a new one. So the new result and the full proof will be in another survey paper for the Missouri conference. So somehow I supposed to submit it in. I mean, as an organizer, always can delay my own submission. So but other people already submitted the paper. Okay, so let's go to our introduction part. So the F be a number field. A of F is the abelian variety. And so we can define this L series. So in the final part, we know the defined by determinant 1 minus Frobenius, and the V, QV negative S, restricted on the tetramodular. This L is different than V of this A, and fixed by its initial group. And more generally, you can start with something more fancy when you start with Artin representation. Of course, you can define a twist function. And the definitions are quite similar, but must be very careful. We have to pick up a ring. So essentially, it's defined by similar way. And this one will be twisted by rho. So the coefficient will change slightly big. And then you will have the BSD conjecture for this one, or even for this one. So you will have that LS rho of A will has a Taylor expansion of R. Then this thing has a lot of things there. You have a torsion part, AF bar, cut off by this rho, take a torsion part, and probably have a dual variety, cut off by rho dual, a torsion part, and you have a regulate. And a regulate is a pairing, the discriminant regulator pairing of between the model value group defined by rho in this abelian variety and other abelian variety. And this R is a rho. R rho is a dimension of A F bar cut off by rho, fixed by rho, and of course tensor with C. So this is the BSD conjecture you want to state. Of course, the reason I put a rho there, because sometimes I may put a rho there. This rho will factorize from extension L there. So essentially, if you have this L of F is a finite extension, then everything is L series. A of L will be some product of this rho of LS, rho, and A. So the reason I put a rho there is because sometimes one piece of them is easier to handle than the whole of them. And even the statement of theorem, they already have some problems. So the two fundamental problems here. So first problem, of course, the analytic continuation of the function. The second problem is how can you evaluate this thing? How can compute the leading coefficient? And the first problem is, of course, related to the modularity. And the second problem, well, in general, it's very hard to do that. So in this lecture, I will spend most of the time to trying to find the good position, good condition of that. So what do we do? We have a basic assumption. Oh, I mean, the case we will work on is that this F will be a totally real field. After a while, you understand why I put F to be totally real. Because you want to do some algebraic geometry. Otherwise, I mean, for analytical part, there's nothing important. But for algebraic geometry part, constructing points, that's actually the hard work. So that means that F tends a real number of a Q is isomorphic to R to the G. So as a R algebra. And the second thing is that A, we assume that it's modular abelian variety of GL2 type. What do I mean is that giving abelian variety, that exactly means, okay, the GL2 type is easy to explain. That means that an morphism ring of A tensor Q contains a field L, which is also totally real. Because the dimension, degree of L, this is a field, semi-simple, totally real semi-simple on algebra of a Q. The degree is the codimension of A. So modular here really means this means GL2. Modular really means that the L series of SA is a product of L series of Fi, I from 1 to G. So this Fi a Hilbert modular form. So in other words, each piece is associated to a representation of GL2. I will spend a lot of time to explain this, what it exactly means, the Hilbert modular form. Then also we assume that I will not consider every row I will only consider such a row which is dihedral. It's a type of dihedral. So rho will be the induced representation from GK to GF of some character. So this chi is a character of Galois group of K bar of K to complex number. Not only that, I will assume this chi is a ring class character. So what do I mean? I mean they're factorized by a class field theory that AK cross, I only take finite part, of a K cross times A cross. So this A is the ideals of F. And ring class character I have times something else. Time compact subgroup is defined by a ring, an order there. This OC is OF plus C times OK. So C is the idea of OK. So that's the situation I will work on. Of course, I mean, there is still a lot of freedom you can do. For example, if you original variety, abelian variety defined of small field, you can make a real base change. Then this situation still apply. But unfortunately, I still don't know how to show when you make a base change, you have a lot of small pieces. I still don't know how to show for this Gross-Zagier type formula for irreducible piece of A over Q. If that could be done, for example, you can redo the cutoff work, because the cutoff work really is a piece of the total real extension. So I will talk about this stuff at the end of lecture. Okay, so this is the situation we can work on. So only freedom, complete freedom is totally real field. Since, I mean, from this one, of course, this is very important. By Fulton's theorem, A object isogeny is totally determined by this Fi. If I assume this A to be a simple abelian variety, then this Fi is a conjugate class, single conjugate class. So I probably start with the Hilbert modular form. So I let N to be idea of OK, OF. And I define a group looks like a gamma naught of N, but I don't write a gamma naught of N. In this group, A, B, C, D is a GR2 of OF hat. So the hat, everything, the hat really means the completion. So my algebra is always finite type. So it's really limit of the alpha m. So alpha is integer. All the m tensor with OZP. The C is a congruent 0 modular n. So this is a group we have. Then we have the Hilbert modular variety, x naught of n. That is PGR2 of F positive and upper plane of G of PGR2 of AF. Somehow, I mean, I always take the center away, but this is not just for simplicity. It's not really that necessary. So probably this one I really needed to say PGR2. So the U0 of n. This looks scary. I mean, this one acts on this one only. This one acts on both. Recall that this one, I mean, this one can be embedded to PGR2 or real number to the g's power. This one acts on each component. This H is a Hilbert, H is a Poincare upper plane. So this is a variety we'll work on. This variety, as a definition, doesn't look like a nice way. I mean, it's very nice when you work on the Heck operators. From a topological point of view, a little bit scary. So what do? The PGR2 of A is actually some elements, alpha I 001 of PGR2 of F dot U0n. This alpha I is represents of F cross, F bar cross, and F head. Let me try to stand. AF cross square times O F head. So in other words, this alpha I, it's just represent this group. This group is the two torsion group. Represents all unramified quadratic extension. So if we don't have many unramified quadratic extension, then this is of course connected. If we do that one, then your variety is not that bad. X naught of n will be, well, you see what's going on is I can replace this thing by this thing. Then you will get the disjoint union of some gamma I. This gamma I don't know which one is which one. So it's basically a congruent subgroup of PGR2. Now I have confused which, I don't know, it's conjugate by either way of the U0 of n alpha I001 inverse. I guess it's no matter because it's order 2. It doesn't matter which way I put. So it's really a union of a usual complex manifolds. And the reason I write this way has an advantage to understand the Heck action. This way, when you do Heck action, the Heck operate sometimes move one connected component to other connected component. Then I give a definition just for today. Tomorrow we'll change another definition. So definition is that, so F is called a Hilbert new form of where 2 and the central for this group U0 of n. That means that the central character is already 0A. If f is called if, let me try to understand. So f is a function. If f is a function from this thing PGR2 of AF to the complex number such that the following property is satisfied. Such that the following properties are verified. So first thing, of course, you want f dz1 dzg is invariant and the PGR2 of f. In this way, this thing will define a modular form, and the differential form of highest degree and variety. Second thing, of course, the invariant, and also you want this one to be invariant, and the action by U naught of n. Okay, the one is from the right hand side, one is from left hand side, and the last thing you want to be well, I needed to probably I should state the actions. You have Z, you have G. Then if you have a gamma there, the gamma U, this action is given equal to the gamma Z, gamma G over U. So I mean, this is the action from both sides. Okay, now let me see. The third condition, of course, I want this form to give a name called omega of f. Omega f is holomorphic, and the holomorphic form vanishes. Holomorphic form on this variety and vanishes at the cusp. And these three conditions just mean that f is a cusp form. Another thing is quite important, that f is the eigenform and the Heck operate Tv for v not divided n of f. That you can write very explicitly. You simply, okay, now they give zg here. It's just fz g and pi v x01. This x is congruent to the modular pi v plus the last term fz g 1 0 0 pi v. So this pi v is a local parameter. You already see some advantage. For example, in the classical case, the action is the left-hand side. You need to put some numbers here or there. This case, you don't need, because this action is totally from the finite place. Nothing to do with the accumulating place. So this way, okay, the 5 is very important. WF does not descend to any x naught of m for m divided n, but m not equals n. So this last one really means that this one is a new form. So this is a Hilbert module new form, but I have to decide what do you mean, what do I mean that new form needed to so of course I want to say the first Fourier coefficient equals 1, but since I will not define the Fourier coefficient today, I simply give you a different normalization. The normalization is normalized as such that the error function is a standard error function. That's the same normalization. So what do I mean? So I put this last one as a property. Is the integration df 1 minus s. This af cross of f cross phi of s0, 0, 1, a to the s minus 1, the cross of a is the L series so I have to explain a lot. What do I need to explain? The following thing. First of all, this measure is a product measure, the cross of v. And this measure, I will not choose, it's not the measure chosen by, I will not choose the measure chosen by Ted in his thesis. The reason is we are doing geometry. We're doing geometry means that we want some compass of a group has a volume exact 1. I don't want to be a half of them. So this standard measure, so when v divided infinity, df is just a dx of x on fv cross and r cross. V not divided infinity, then the dv, I want the volume of ov cross to be 1. So it's slightly different. You need to normalize it by some error function. Then you get this normalization by Ted. So it's different than Ted. The Tamagawa measure or whatever. The standard Tamagawa measure, of course, is a Tamagawa measure of some convergence factor, but not a standard one. In this way, the reason is this way is compatible with class field theory. You get a volume 1 exactly. You have a simple counting. Then I have to define the local effect. This local effect has 3 parts. If V does not divide n infinity, it's really the standard one. 1 minus lambda V QV negative S plus QV 1 minus 2S negative 1. So the QV is really the norm of pi V inverse. If V divided infinity, then I get 2 pi negative S, the gamma S. Well, this is very close to Tether's one, but it's different than the paper I wrote down. I put 2 everywhere because as a Jacquet Langlands use 2. Sometimes put 2, sometimes not put 2. But doesn't matter, it's since my formula eventually one side has an inner product of phi, other side error function. So if you decide to take 2, you take 2 all the time. Otherwise take it away. So it doesn't depend on your 2 or not. So sometimes put 2 or not. So only reason put 2 because there's a Rankin error function. Once you put 2 there, it's more convenient. Put V divided n, then it's 1 minus lambda V QV negative S. So lambda V here will be either 1, negative 1, or 0. So that is the theorem. I mean, that really includes all the definitions inside. Now I don't know what I should do next step. Okay, this is a Hilbert new form. So the proposition. Oh yeah, the last one is really not there. I mean, I'm sorry. So I get a lot of I don't know what I write down. Some of them the definition, some of them really the consequence of definition. It's not really. So for example, error series here, it should be next step. Should be next one. I wrote too early. So so the proposition? Well, I write it down. So we define Z of F to be the integer joined with all these lambda V. I'm sorry, I didn't define lambda V. Lambda V is eigenvalue of Heck operator. So TV of F is lambda V F. The join, so this is a complex number. So this is a subring in complex number. So the first thing is this ring is a total real number field of finite degree. Total real field, total real is totally real of finite rank. I mean that every conjugation of these numbers are real. This follows from the self-joint property of the Heck operator and the finiteness of the well, you have to do that by cohomology somewhere. The second property is something called a strong multiplicity 1, but I just put it in the same way. The second thing is the following thing. For any embedding of Z of F to the real number, of course, I mean, you have one embedding already. Now you can put some other embedding. There is a unique new form called F sigma, such as that the TV of F sigma equal lambda sigma V sigma of F sigma. Where the third property equals 7 in the definition. So the definition is the last property in last definition is not really part of definition. It's a part of the proposition. So this is the definition of Hilbert modular form. It's very similar to the form in over Q, almost no difference. Yeah, I mean, the fact about the L function is really part of this proposition. Now I want to state the main result. The arcular Shimura type sin. I mean, we will prove this theorem at there later on. I mean, at least sketch the proof that so let F be a new form. Well, this notation is a new form. So this is a, I'm sorry, be a new form. For U0n, assume that a two property either this field is odd or this n is not a square. I mean, the sum factor is square free. Then there is on abelian variety of F, the simple abelian variety of GL2 type of GL2 type such that the L series of A must be very careful. L series probably I have to exclude the beta factor of the n. Probably is proved by Carillon already. So anyway, is a product of L series of this n. The sigma from Z of F to complex number. And moreover, so this A has anamorphism by Z of F. And this ring and the dimension of A equals the rank of Z of F. Of course, you can read it from here. So if you really want a Taniyama-Shimura type conjecture, well, the converse of this thing should be called Taniyama-Shimura conjecture. I don't know this condition yet. These two conditions are very subtle. For example, if this condition is not true, then it's not obviously how can we construct an abelian variety to a given Hilbert modular form. Even the Hilbert modular form has n Riemann everywhere. I guess Richard Taylor and many people have already constructed the system of Galois representation, but they could not construct the abelian variety directly.
Is the second condition really optimal? Non-being squared could be weakened, no?
This one.
Yeah.
I say either or.
Yeah, but in the case when the dimension is even.
Dimension even, you must assume n be, I don't know, I mean, in the case I. You will see this is exactly the condition Jacquet Langlands can carry out. So I will tell you, later on we will prove this theorem. My conjecture, I know that a lot of more experts than me. The converse is true. I mean, assume this condition, every abelian variety of GL2 type should be this way. I mean, must be say simple. Well, as simple. So assume this any. So if as simple GL2 type. Simple is important because if not simple is a product of several of them, then you don't know something could be missing. GL2 type, and the conductor is n, and this is not a square if f of q is even. Then it's modular. in this sense. We will give a more precise meaning of modular sometimes later. Well, one remark is quite important is say this A, suppose I give a name called this A. A cannot be constructed by integration on x naught of n. Okay? I mean, you integrate this form, and this form is the form where G, form of degree G. So probably you get some intermediate Jacobian, then actually probably get some piece. The cohomology or motive of this abelian variety will appear in the middle cohomology of these Shimura varieties, but not the abelian varieties itself. Okay. Okay, so now we have the modular form, and we want to define. So now we want to talk about the Rankin area series, or Rankin-Selberg area series, depends on where do I talk. Somebody say, well, it must be talk Rankin. Sometimes I have to Rankin-Selberg. So we start with the K of F, the total imaginary. And with the chi, the ring class character. So it's some Galois representation of HC of K to the complex number. So this HC, this one, as I write down, is really Galois representation. It's really a K cross of just take a finite part, K cross, A cross, and OC cross. So I call the ring class character. It's slightly more restricted than the anticyclotomic. It depends on what you mean anticyclotomic. Anticyclotomic really means that you will not restrict this one to be trivial rather than the norm of the K of F, a K cross. So this one, if I put this one inside, that will be anticyclotomic. But this one, I don't know much. Maybe it should call dihedral. But this anyway, this is a character I will discuss. So C, or assume this C is a conductor of chi. So in other words, this one will not be factored through any smaller c. Now I assume that, well, this assumption is not important, just for a reason I can define everything very precisely. The discriminant K of F, the conductor of the form, and the C co-prime each other relatively, I don't know what you say, pairwise, prime, co-prime. So I define this D to be C squared times dk of F. I mean, this D, of course, we have a million letter. Then I can define the Rankin-Selberg error function. This will be a product of V, Ls, chi, and F, the local representations, the local factors. This have two way. I mean, have two way to define it. One way, you leave your series of F to K, then twist by chi. Another way, you do the Rankin-Selberg. So I decided to take a second way. because I wouldn't want to move my form to K. So this LV S chi is really LV as induced representation of chi and the F. I mean, of course, this is also equal to LV S chi. You basically change your field to K. So this is a tensor product. This is also a tensor product. Let me try to define this thing. So you have 3 parts. One is V divided infinity. That is quite easy. 2 pi negative 2s gamma s square. So it's essentially the L function at f, just take a square. V not divide infinity. Then what do? You just product 1 minus alpha I beta j of qv negative s negative 1 ij. So how to define this then? So where Ls f is written down as the product 1 minus alpha v alpha 1 q negative s 1 minus alpha 2 q negative s, and LV of s induced representation of chi, which is equal to the product w, the factors of the places of k dividing v of this Ls chi w. So sometimes they have 2, sometimes 1, right? Equals to, you just write down, decompose it this way. Beta 1 q of negative s 1 minus beta 2 q negative s. So it's really kind of convolution in the sense that if we write this one, the determinant of 2 by 2 matrices, write this one 2 by 2 matrices, then the L function here is a degree 4. It is the tensor product of 2 matrices. So you have degree 4 L series. So of course, then this one is defined to be the 2. I mean, I didn't define, I keep it in place, but I still can define that. 1 2 pi. Let me see. Negative s gamma s. If v dividing w divide infinity, if w divide c, you get 1. W does not divide c infinity, you get 1 minus chi w pi w qw negative s. So what we can do with this series is the following thing, that we have an L function. So this L, S chi f will have holomorphic continuation to a whole complex plane. I mean, this is the next lecture. We will see the proof of that. And satisfy a functional equation is functional equation as sigma negative 1 to a set sigma kn. We define later the norm of this n times d 1 minus s and L 2 minus s chi f. This sigma k is a final subset of places of f is determined by these 2 numbers. Either v divide infinity, I'll keep it in place, or v does not divide infinity, is inert in k, and all the v of n is odd. So this L function has a complete description once the n and k is given. So this is why I call it sigma kn. So we have two cases to concede. So now is the case if you want to think about the measured conjecture or general phenomenon, you see that there is a sign, positive and negative. So 50% should be, I mean, the LCS should not be vanished unless be forced by the function equation. Here it must be very careful because the Galois representation defined by Kant and F may not be simple. So if you want to apply that principle, it's only applied to when induce a representation of chi and the Galois representation associated to F is simple, because then your L function will not be decomposed further. Otherwise, you have some exceptional case described in the Mazur's ICM lecture. So that's exactly the case that is a representation you cannot detect by function equation because the reduced one to Q will be reducible. So I will not going to talk about that. Then you can look for my survey paper about this point. So you have two cases. So either this sigma nk is even or odd. So now if you go back to think about the Heegner condition, we listen so much in these lectures. What does Heegner condition say? Heegner condition say that every prime of P divide and split. That means that these things totally disappear. So if this whole thing disappears, it's called a Heegner condition. But I mean, from L function point of view, we see this is not really a natural condition here. And but this thing will be very important to construct the Shimura curve. This is exactly why we moved the Shimura curve, because this one may not be trivial. Even this one is trivial is not obviously one. I mean, if this one is trivial, it will be some case of the modular curve case. So this is about L series. I mean, this we will spend a lot of time on this in tomorrow's lecture to prove the theorem. Now I'll talk about Shimura curves of NK type or level NK, whatever. So this is really analog of X naught of N over Q. So what do you do? So now we assume this sigma nk is odd. We will do even case later. Then we fix a place tau of f. Then there is a unit after isomorphism, of course. Quaternion algebra. B with ramification set equal to sigma and k, take this place out. This Archimedean place. Well, for this issue, I don't know what's the lecture note. What is the lecture notes? Quaternion algebra 249. Yeah, you should go to this book. It contains everything about the quaternion algebra. So this B can be constructed by the following way. I give a simple way to write down this stuff because the quaternion algebra, usually if we don't work on. So this B you can write down as the F joined with two numbers, square root of D and square root of something else, square root of B. I don't know what's the letter I should write down. M. So the M is F cross. M is the inside the norm of K of F of the KV cross if and only if V is not in the set. So you can pick up such a element M, take this place out, and of course, be careful. Square root of d times square root of m equals negative square m times square root of d. It's just a quaternion algebra. So this is an even set. In other words, you think about the Hilbert modular, Hilbert symbol. I mean, this equals 1 if and only if v is not equal to this thing. It's not inside that thing. So the construction. So one thing is very important, that the v is split in K implies the v split in B. So what that means? So that means that there will be, so that one can find, so there is a embedding of the K inside B. Now I define a G as algebraic group B cross of F cross, the algebraic group of F. So in other words, if you think any algebra A will be A tensor B cross divided by A cross. And later on, actually, I will think of this G as an algebraic group of OF instead of F. So to do that, I have to fix some order. So the fixed order OB containing OK. So in this way, I can think of my group not only of F, it's actually over OF. Now for any open compact open subgroup of G F A F, we will have a Shimura curve. We have a Shimura curve. XU equals G of F positive of H, G of F, take a U out. So this is the Shimura curve. So the XU is actually defined of F canonically. Where you will see that XU does not parameterize any abelian variety, but if you replace this G by this E cross tensor K cross of F cross, then this actually is the U11, GU11. So this actually parameterizes some abelian variety. Then this Shimura curve is embedded to that Shimura curve. Somehow, I think de Gross believe this one is much natural to work on this thing because it's already parameterized abelian varieties. But unfortunately, the reduction is more complicated than this one. Then I've not yet decided, so we need to specify our U. So what is our U is? So let R be an order of, so U will be order of B containing OK with relative discriminant n. Then our U will be, in the completion of this n, the modular OF this n. So, I mean, maybe you ask me how can I construct this thing. This actually is not that hard. The reason is R can be written as just like a usual order you write down. OK plus some idea times OB. And this idea is norm times the ramification of this B is exactly n. That's exactly those place which is not norm from K becomes the part of the ramification of B. Okay, so this is R, the construction of R. And so what's going on? Let me see. How can you see that in the Heegner condition, where implies is B equal matrix of Q, that this R is nothing, is isomorphic to the usual, the actual order. And if you weaken your Heegner condition slightly, you say, I want to, every P inert, the P inert in K implies order of P of N is even. So second set, this B is still M2 of Q, but R is some kind of non-split actual order. Non-split, I mean that when you make some base change, it will be exactly like actual order. By itself, it's not. What? Oh, this N is idea. Yes? What? No, I don't understand what you talk about. So I write this one, I give a name called U and K instead of a U0 N. So we have two things. This U and K very depends on K. It also depends on N. The part cannot be defined. Cannot in the sense that this order is not unique, but its completion is unique. So in other words, any other order is kind of an invertible modular of the, I mean, it's locally isomorphic to the R. It's a kind of genus. Wow, where we are? I don't know. I can't have a. Seems like finish only. Well, let me try to. Probably I could not finish it. Just stay a little bit. So what's going on is that. Now I know what I'm going to do. I mean, I cannot finish this. At least I can finish something else. So. So now we have a theorem. Plus, of course, the Jacquet Langlands. The plus many people, I should say. I mean, all this work come together, put together to prove the following thing, that there is theorem 1 theorem, there is a unique modular form S2 of U0 of NK, the where-to form F prime, which has the same eigenvalue as F and Heck operator TV. So at least the Hilbert modular form and the Hilbert modular variety suddenly transform to a modular form of the Shimura curve. That is very important. The reason is then we can use this form, or actually the Heck character, to cut off the Jacobian. So next thing is quite important. So there is a unique abelian. I don't write this in. So let me define this AF prime to be the Jacobian of the X and K type, the tensor of the ZF by the Heck operator. So this will be abelian variety. You take the, I don't know what is the dual, to the self. So this will be embedded to Jacobian X and K. Then the L series of F will be the product Ls F sigma. Okay, so at least we schedule the proof of Shimura theory. So exactly here is unique. Maybe there's one minute. Maybe you want to ask, how can I parameterize? Is there any way to parameterize this n to AF? Just like what we do in abelian variety. In modular curve case, what do? We have a cusp. Every point minus cusp. Here, we do similar thing. The parameterization, the modular parameterization is given by following thing. Modular parameterization is taking the X, goes to the class of X minus Kc. This Kc is what I called the Hodge class. I mean, at least that's a faster way, the elementary way to explain this Kc. Faster way, you replace the Shimura curve by high level so that there's no fixed point. Then you have then you can define your Kc will be the, well, let me try to, I'll give a description. So what's going on is this X and K will be just joined with upper plane modular the gamma I. And this Kc will live in the Picard of this X of degree 1, 1, 1, 1, 1 because of many components, all ones. So the Kc will be Kc1, Kcn. This Kci is a standard bundle given by omega xi. This is up, take the cusp, if you have a cusp, okay? Plus summation 1 minus 1 of E of x, and divide by the integer. So this is really tensor with Q. And this is I. This is E of x. Is a cardinality, a stabilizer of x inside the gamma I. So you get some class. I mean, it's I don't know which one is canonic, but at least one is going to define it. So I give a definition. So pi is called admissible if pi of Kc, some multiple is 0 for some n bigger than 0. So you get a class of parameterization, not one of them, but this one is equally good. It's very similar to the one we parameterize the elliptic curve by cusps. But this one we parameterize the elliptic curve by the Hodge class. Great, I guess maybe I'll stop here. I will continue tomorrow,